Yeah, good morning, everyone. Apologies for the delay in starting and also for the rescheduling of the event. I had a family emergency, which turned out all right in the end, but it was last minute and had to take someone to hospital and couldn't hand over the reins in that short period of time. But thanks for being patient and thanks for joining this week. The technical glitch, we've got the presentation slides up. This is being run by Esanda Engineering, and Dem Dimitriou, he works with us as an associate, and he'll be talking to you about SURF, subsea umbilicals, risers and flow lines. I did have a few introductory slides, which we'll skip to avoid holding everybody up because of the technical issues. Generally, we'll take questions throughout the talk by chat, and at the end of it, we'll have time for more questions and answers. During the talk, though, I will try and answer what I can. I do know a little bit about SURF, not as much as Dem. So what I can't answer, I'll hand over to him at the end of the talk and maybe get him to clarify or check that I'm right in what I'm saying. But yeah, without any further ado, and I don't have my slides in front of me to talk to, we'll hand over to Dem. And I'd just like to say we are recording this session, so it will be available on YouTube after a day or so after the talk. Okay, so Dem, I'll hand over to you and you can do a short introduction to yourself and get on with the presentation.
Yep, good morning, good afternoon, everybody. Thanks on the start for the introduction and the opportunity to give to subsea risers, umbilicals, and flow lines. So it's an overview of the subject area. We'll cover quite a lot of ground in this sort of 45 minutes to an hour. But if you need further information, please don't hesitate to contact me. So a little bit about myself. I've been in the oil and gas industry since 1990, specializing in subsea pipeline and materials engineering. I've worked with major operators, BG, OMV Petrom, and others, and also with Genesis Oil and Gas Consultants in the UK, involved at all stages of development. So my background is actually materials engineering, but I've spent most of my life, in fact, all of my life, working life in subsea pipelines and subsea engineering. So I'm accredited by the Society for Underwater Technology in the UK as a subsea engineer, and I'm also a fellow of the Institute of Marine Engineering Science and Technology. Just a very brief background. I work for a company called Argo Energies. So we're an independent consultancy, and we provide management, project management, engineering services to the energy business, specializing again subsea and pipeline engineering. So the agenda for today, we're going to look at some of the key components of subsea umbilicals, risers and flow lines. So we're going to look at subsea trees. We're going to look at subsea structures, so manifolds, templates, plets, plems. We'll look at different types of flow lines and pipelines and try and briefly introduce the difference between them. A very quick look at spools, jumpers, and also risers, and then finishing up talking about subsea control systems and umbilicals. And then I'll try and draw that all together towards the end of the presentation by looking at it from a holistic systems engineering point of view, overview. Okay. So firstly, this is a typical subsea development. So you can see, sorry if I get my little pen here. So you can see here is a host facility. So in this case, it's a tension leg platform. And you can see coming down from this tension leg platform, we have some flow lines, so dual flow lines connecting to some pipeline end terminations or plets. These plets then are connected to a manifold, and the wells are also connected to a manifold. So this is a typical configuration that you might see a number of wells clustered around a central manifold to provide the production flow back to the host facility. And also, in order to be able to control these wells, we need to have some kind of umbilical, which usually provides power, hydraulics, chemicals to the wells. And so the umbilicals linked by means of and the thing you'll love about subsea engineering is the preponderance of 3-letter or 4-letter acronyms. So SDU is a subsea distribution unit. So the umbilicals connected to a subsea distribution unit. And from there, we have either EFLs, electrical flying leads, or HFLs, hydraulic flying leads, that connect from the subsea distribution unit to the Christmas tree in order to be able to control production from the wells. Okay, so these are our basic building blocks. We're going to look at each of these now in turn and discuss a little bit about them. Okay. So first component we're going to look at are the subsea trees. And so the subsea trees, the primary function of the subsea tree is to control the production of hydrocarbons, be it oil or gas, and monitor those from the subsea well. Tree and also allows you to the well necessary. The Christmas tree also needs to have injection points for chemicals, so it might be a corrosion inhibitor, it might be scale inhibitor, it may be methanol for hydrate inhibition. So all this functionality needs to be accommodated by the Christmas tree. And here you can see a typical Christmas tree with a ROV interface panel here. So the ROV can actually access and operate the valves on the Christmas tree from this ROV panel.
Excuse me, Dan. Maybe turn off your video because you're breaking up occasionally. Hopefully that'll help with your bandwidth.
Okay.
Not sure, but we'll give it a try. Yeah.
Stop video. Okay. Is that better?
So far.
Okay, good. Sorry about that.
That's all right.
Okay, so we're going to go on to look at the so there are two main types of Christmas tree. The first is horizontal Christmas tree, and the second is a vertical Christmas tree. So the main difference, or the only difference between the trees, is the arrangement of the wells. So of the valves. So in the horizontal Christmas tree, so these are the original kind of first generation Christmas trees, if you like, adopted from, sorry, I've got that wrong way around. Sorry, the vertical Christmas tree is the original developed from the land Christmas trees, onshore Christmas trees. So these have all the valves in a vertical arrangement. So you can see that if you need to do some kind of maintenance to the tubing hanger or the wellhead, then you need to basically access the tree. Then you'll need to go through this bore here and use some kind of means of access. The horizontal Christmas trees were developed a little bit later on, and instead of having the valves stacked up vertically, now some of the valves are moved horizontally. So this allows easier access to the tubing, so allows you to retrieve the tubing hanger and carry out maintenance on the wells without the valves being in the way because they're stacked sideways. And it's a little bit of an operator preference as to which tree is used. So as I said, in the early days of subsea engineering, the conventional tree was used. In probably about the 1990s, horizontal trees became more and more popular, which allowed easier access for well intervention. The fashion seems to have kind of flipped recently now, and conventional trees are being used more increasingly commonly. So it's a little bit of an operator preference. Both have advantages and disadvantages. And as with a lot of these decisions, it really comes down to the specific circumstances, plans for workover, plans for maintenance, how you intend to operate and maintain the wells going forward in future. Okay. So looking at it from a production point of view, a P&ID point of view, so this is the same horizontal tree that we had before, and this is the P&ID, so the kind of the process description, if you like, to help you understand it a little bit better. So we'll have some DHPTs, downhole pressure and temperature gauges, so this allows us to monitor the well. SSV subsurface valve. So this is the valve that's set to basically to shut in the well if there are any major operational issues. We have two kind of sides to the Christmas tree. In green, we're showing the production side, and in in purple is the annulus side. So the annulus allows you to have access into the main bore if required. So just to go through again some of these acronyms, PMV is the production master valve. So this is the main valve that controls the flow. This is the production wing valve. So the production wing valve allows us to have access into the annulus, and the PCV, production choke valve. So this is the valve that controls the flow. So we adjust the choke valve, all these valves are hydraulically operated, and we adjust the choke valve so that we can adjust the flow from the well. Again, we have some temperature transmitters and some pressure and temperature transmitters, both upstream and downstream of the choke, to allow us to monitor production. And on the annulus side, gives us access to the well bore for intervention for maintenance or to recirculate fluids. So again, we have the annulus master valve, the annulus wing valve, and this is the annulus access valve and the annulus choke valve. And controlling all these, we have the subsea control module, which sits on a subsea control module mounting base. So this is our basic tree. This is our basic P&ID. It's usually modified depending to have various injection points for the various chemicals that I mentioned earlier. But this is the basic configuration of a horizontal tree. So the next component I want to look at are the various subsea structures. So we're talking about the various manifold systems. So here you can see this is our well, and it's tied back, or different number of wells here, and these are tied back to some kind of manifold. So a manifold is really there to gather flows from the different wells, to commingle flows if necessary. Sometimes it has pigging functionality to allow us to round trip pigging. So there may be a pigging loop contained in this manifold to allow round trip pigging around the system. So manifolds can be pretty big. So here's an example of one in a yard. So we can see here the pipe work within the manifold, the valves. You can see the ROV interfaces here to operate the valves. This this manifold structure here is designed to be over trawlable, so this is designed to resist any interaction from fishing gear. So we can see it has sloping sides, typically about 45 degrees, so we don't get any interaction with fishing gear. It also has a roof panel here. So you can see this roof panel is typically made either of steel grating or more recently GFRP, glass fiber reinforced plastic grating, to provide any protection from dropped objects. And these roof panels may or may not be removable to allow you to recover and to retrieve any valves. And you can see here, this is the lifting strops ready for this to be lifted. What else can we see? So we can see here we've got the pile receptacles. So this will be piled into the seabed on the and put into operation. And this is, this gives you a nice idea of the scale of a manifold. They can be big, they can be much smaller, depending on the number of wells that are going to be produced. Templates are slightly different to manifolds. Templates will have the capability to drill through the templates. So the templates are set on the seabed. You will drill through the template, and actually the Christmas trees will be installed within the template as well, and they will have the same as a manifold as well. It's already also set on it. This is this believe is the sorry, it's the same as this one. This is the Ormond Langer template, which was installed in Norway. So this was installed in about 900 meters water depth. It's about 1,100 tons, and it's about 44 meters by 33 meters, and I think it's about 15 meters high. So this is one of the largest ever templates has been installed. So real kind of massive beasts. So the functionality, so we can, as I said, they're there for commingling, distributing fluids, diverting flows, controlling pigs if necessary. So here you can see this has a loop that you can potentially use for pigging or recirculating flow. Can also be used for providing isolation, so you can shut off different wells if you have actuated or even manually operated ROV operated valves in the structure. Can be used for cooling if you need to cool the fluids, and also for protection and housing of the Christmas trees. So a bit about terminology, manifolds or templates. Some people get these confused. So as I said, templates locate and house wellheads and trees. That's the fundamental difference. So a template will include the wellhead and the tree, whereas the manifold won't include the template, won't include the wellhead and the tree. The templates usually include some manifolding pipework, and they are installed before drilling commences. So that gives you some schedule constraints in that you have to design and build the manifold before you start before you can start drilling. And as you can see by the size, they often need heavy lift vessels to install them. Manifolds can be installed at any time. They're generally smaller, lighter, and easy to handle. Can have wells remotely located from the manifold, but the disadvantage, of course, now is that there's significant hookup work. We have to connect each well to a manifold. So if we're drilling lots of wells from the same location, the template might be a good idea. If we have to drill wells around the field because of the nature of the field, then we have to connect them back to a manifold. They can be fishing friendly, they can be over trawlable, or they can be neither. So over trawlable means that the fishing gear must be allowed to go over and not interfere. Fishing Norsok Norwegian standard, and this kind of should include members that deflect to allow fishing interaction. And flat-sided structures are acceptable where there's no fishing. So, for example, if you're under an FPSO, there's unlikely to be fishing, so you can have a flat-sided structure. This is an example of a GFRP protection structure. This is actually sits over a tree, I believe, but it gives you an idea of the design for a fishing-friendly or over-trawlable structure that's necessary. So moving on from structures, the next component are our flow lines and pipelines. And again, there's some confusion in terminology, and people kind of these terms interchangeably. So flow line, field lines, and what we mean by infield lines are that they might be between a manifold and a host, or between manifolds, or from within the same area. So they're typically smaller diameter, and they typically have multi-phase production, whereas pipelines usually refer to an export line carrying processed fluid. So it might be processed gas or processed oil, and usually it will come from a platform or a facility and go to the shore. So sometimes also referred to as a trunk line, but as ever, interchangeable use. It's not really a very big deal, but these are kind of the strict definitions. So our flow lines or our pipelines can be made from a number of different materials. They can be and in different configurations. So we can have a conventional steel pipe. We can also use clad pipes. So this is where we have a carbon steel pipe with a clad layer of corrosion-resistant alloy to improve corrosion resistance, corrosion performance. We can also have non-bonded flexible pipes. So this is non-bonded flexible pipe. So this consists of a series of different layers of, you can see here, this is a wire armor with polyethylene, and then a series of wire armor wound in different directions to give strength in bending and also in pressure containment. And then there's an outer protective sheath, usually again in polyethylene or polypropylene or some other suitable material. So non-bonded pipe, or flexible pipe as it's sometimes known, are used quite often. Disadvantages are only available in sort of smaller diameters and have sort of diameter, temperature and water depth limitations depending on the manufacturer. We can install pipe as a piggyback, so where we have a smaller diameter line installed strapped to the back of a larger diameter line, or we can also install what's known as bundles. So bundles feature a number of different pipes in a large outer diameter carrier pipe. So the carrier pipe might be, I don't know, 50, 55, 56 inch diameter. And within that, you'll have smaller pipes. You'll have a production pipeline. You may have water injection, methanol, and you'll also have the components that you would normally have in an umbilical. So you may have your hydraulic hoses and your electrical cores within there. And the bundles are fabricated onshore. The length is usually around 6 or 7 kilometers, limited by the length of the fabrication site. And we have this tow head at the front, and we have a trailhead at the back, which will look similar to this, which has buoyancy, and these are actually towed out to the field using some anchor handling tugs. So it removes the need for a very expensive installation vessel, a very expensive lay barge. So these can be towed at different locations, either just off the bottom surface, or sometimes on the surface initially pressurized with nitrogen, and then when you get to the field, you flood the bundle and it sinks to the seabed. So, number of different kind of technologies. In terms of installation, the sort of 3 or 4 main ways of installation are S-lay, J-lay, reel lay, and the tow that I've just mentioned, controlled depth tow. So you can see an example here on the right is S-lay. The reason it's called S-lay is that the catenary of the pipe that hangs off the back of the barge typically takes this S shape. So sections of pipe are welded on the barge, and they're supported as they go off the back of the barge by this stinger, and held in place by some tensioners on the lay barge. And as sections of the pipe are welded, the barge moves forward and lays down a section on the seabed. Some J-lay, again, the name comes from the shape of the catenary on the seabed. So instead of an S, it's more of a J, so it looks sort of more like this. Much steeper configuration. And this case, the welding is done in the vertical. So you can see here, there's this J-lay tower, which upends pipe, and the pipe is welded in the vertical position and lowered down onto the seabed. So J-lay is much slower than S-lay. S-lay, you may be, 3 to 5 kilometers a day, whereas J-lay might be 1 to 1.5 kilometers a day, but it's much more suited to deeper water, larger diameter pipe. The other method of laying pipe is what's known as reel lay. So here in reel lay, pipe is fabricated on shore into typically 1 kilometer long stalks. These stalks are then welded together and reeled onto this large diameter reel onto the lay barge, and then the boat sails to site, and the pipe is unreeled and laid down on the seabed. And reel lay is quite interesting because you're actually, as you're reeling on and reeling off, you're actually plastically deforming the pipe, I think 3 or 4 times during the reeling on and reeling off operation. So there are sort of more stringent material and welding requirements for reel lay than there are with S-lay or J-lay.
Excuse me, Dan. How many kilometers a day would you get with the reel lay?
The reel lay, it's literally just chucking it over the side, so it could be, you could be 10 kilometers a day. It's really quick. The disadvantage, of course, is if you have a long length, then you're limited by how much length you can take out, limited by the weight capacity of this reel. So typically around, I can never remember numbers, I think it's about 200, 300 tons that you can take on this reel. So what you may have to do is to go back and reel on more pipe. So that can add to the process. So reel lay is great for shorter lengths and smaller diameters, up to about 14, maybe 16 inches, the maximum that you could use, that you can use for reel lay installation.
Okay, thanks.
Okay. So much quicker, great for shorter, small diameter. Lost my cursor. Two other kind of acronyms to watch out for: plets and plems. Again, sometimes used interchangeably, but pipeline end terminations and pipeline end manifolds. So pipeline end terminations installed on the end of the pipeline, as the name implies, and they're usually there to provide, usually used for deep water developments, and they're usually there to host a diverless connector hub. So we need to connect the end of the pipeline to something, and the pipeline end termination will have that connector in place. It's installed during the installation operation as part of the pipeline. It's touched down on the seabed, and then we can use that to connect to the tree or wherever we're going to. Pipeline end, so the plet is typically very simple. It just has a connector, whereas a plem can be more complicated. So it can include connections to other facilities. It might include provision for pre-commissioning activities such as pigging, dewatering, and it's generally installed as an independent structure because it's a bit bigger and a bit heavier. But sometimes, again, these are used interchangeably, so just something to be aware of. So here's some typical pictures. So here, this is a pipeline end termination. So you can see here, it just has this single connector. So the pipeline here you can see the connection sort of being made up in the yard, so being trialed in the yard, and the same here. And the pipeline end manifold, so you can see this is a little bit more complex now. It has some valves and pig launcher or pig receiver to allow for some pre-commissioning, dewatering functional activities to be carried out. So plets, very simple, single connection. Plems, a bit more complicated, can have different components within them. So spools and jumpers, very brief. So spool and jumpers basically connect the components together. They can either be diver installed or they can be diverless. Obviously, in deep water, they will be diverless. So that makes things a little bit more complicated in that we have to have these kind of diverless connections. And then we need to decide whether the spools or the jumpers will be vertical or horizontal. And then we need to, they have an odd shape or may have odd shapes because they need to accommodate thermal expansion, installation tolerances, misalignments, connector alignments. So they need to be designed to accommodate the various forces that we will see, so that they don't transfer loads onto the equipment. So here, this is one that's been installed. This is quite a large spool. You can see there's a number of lift points connected. So this is a U-shaped spool designed to accommodate expansion. So you'll get expansion from either side, and this spool gives some flexibility to accommodate the expansion. And again, this is a similar one. You can see this kind of characteristic shape to give some flexibility and to accommodate expansion. This one's installed by ROV using diverless connectors. Risers, so there are lots and lots of different types of risers. Risers can be rigid, so rigid platform risers. They can be flexible, made with the flexible type that I mentioned before, particularly suited for large diameter deep water FPSO developments, or they can be hybrid risers. And they can extend over quite a large distance. So this is an example from the Nakika project in the Gulf of Mexico, and these are the risers, and you can see they're overlaid over a map of Houston, because someone in Texas did this, I suppose. So this is downtown Houston, and you can stand for 2 or 3 kilometers, particularly in deep waters, in extent. So again, we need to bear this in mind when we're setting out our field layout. Where do we install our end terminations, our riser bases, our flow lines? How do we design this architecture in relation to our wells? So I'm just going to go and come back. So flexible risers, different configurations. They can be what's known as installed in an S configuration. So in this case, when they're over an S configuration, they will go over some kind of arch. So you can see here this mid-water arch, as it's known, and you can see the mid-water arch sits tethered to the seabed at some depth, and the risers are installed over the arch in a continuous manner, and touch on to see some distance away. So here's the mid-water arch. The other way is in a wave configuration. So this shows an Orcaflex model of a flexible risers in a wave configuration. And here there's no mid-water arch, but the red area denotes some discrete buoyancy. So buoyancy is added to maintain the this kind of flexible wave configuration. And again, choice comes down to various factors, but environmental conditions mainly, water depth, size of risers, number of risers, and so
Tim, we lost you there.
Section.
Sorry, excuse me. We lost you there when you were talking about the discrete buoyancy.
Okay.
Yeah.
Sorry. It's okay. So the wave configuration is maintained in this configuration by having discrete buoyancy elements attached to it. So the red section here will be an area that there is some buoyancy attached, so it maintains it in this configuration, and the choice will be dependent on the choice between these kind of configurations will be dependent on things like water depth, environmental conditions, number of risers, interaction with neighbouring risers, etc. And just going back to this one, so this is a hybrid configuration that was used on the Girasol project in West Africa. So this has rigid risers which are tethered to the seabed, some distance away from the FPSO, and then from the top of this rigid riser, there's a flexible that connects from there to the FPSO. So this is quite a unique hybrid solution that was used in the deep water. Platform risers, so reasonably straightforward. If we're building a new platform, then we can design the riser and install it during construction of the jacket, and it gets loaded out with the jacket. More often, we're looking at retrofitting risers to existing structures. This becomes more complicated. We've got to look at where they can be installed within the jacket riser, within the jacket, or are they clamped to the outside of the jacket? And then we have to have shipping packs, and then we have to work out how we're going to install it and look at how long it's going to take. So here's an example of a prefabricated riser being lifted into an existing jacket using winches from probably from the platform and from a DSV which brings site. The next area to look at is the control system. So we've got all this equipment on the seabed, but without a control system, it's kind of effectively dumb. So we need to have some way of opening and closing valves on demand, closing valves in an emergency. So if there's some kind of emergency condition, either with our field or with an adjacent field or some issue on the host, then we need to be able to close the valves. We need to also be able to monitor things like pressure, temperature, flow rates, corrosion, erosion, and the status of the valves. And the control system also needs to distribute chemicals to the wells or to the phones in the field. So it's kind of really that these are designed appropriately. There are lots of different types of control system, but the one you'll most commonly see is this one I've highlighted here. It's the multiplexed electro-hydraulic control system. So where you've got a short distance between your subsea host and your well, then direct hydraulic could be used. So you have valve. Disadvantage is that it's slow response times. So I guess most modern control systems, most modern fields have what's known as a multiplex electro-hydraulic control system. So we use hydraulic, the valves. Can be used for long lengths, hundreds of kilometers. Umbilicals small. So, even for quite a complex system, the umbilical diameter might be, I don't know, maybe 6, 8, 10-inch diameter. So not really a very large size. So there's lots of other components of the subsea control system. Some of those components are on the top sides, on the host. So you will typically have a hydraulic power unit, an electrical power unit, providing, as the names imply, hydraulic and electrical power to the system. There'll also be an MCS, so the master control station. So this will be a computer terminal in the control room. These are all interfaced to a topsides junction box, sometimes known as a topsides umbilical termination assembly or topsides umbilical termination unit, TUTA, TUTU are the names that you might hear. And from the topsides junction box, the electro-hydraulic control umbilical is connected to this subsea umbilical termination or subsea distribution unit, as we saw earlier. And the cores are split out, so the electrical and the hydraulics are split. We connect these to a subsea control module, SCM, which sits on a mounting base, sometimes, not always. And in there is an SEM, subsea electronics module. So this is the electronic brains. We have the electrical actions, flying leads, sometimes known, or jumpers components, but were actually well proven and reasonably good reliability. So just to finish up, then looking at the umbilical. So the umbilical links up all the control system components. It distributes hydraulic fluid, transfers power and signal, and supplies chemicals for injection. So here's a typical cross-section of an umbilical. So what can we see here? So we can see the umbilicals can either have thermoplastic hoses or steel tubes within them. Typically, steel tubes are used for deeper water applications because of their better resistance to external pressure. And so here you can see the various hoses within there. So these are the main hoses. You've got some other hoses here, and you can also see the excuse me, the electrical cores here. So you can see electrical cores. So typically we'll have high pressure and low pressure hydraulics with dual redundancy. We'll have electronic, copper and have fiber optics within the umbilicals recently. So you've got these cores. Sometimes they'll have fillers within there made of lead or some other material to add weight. And then we've got this armoring around here to give resistance and strength. And finally, an outer sheath of something like polyethylene to provide mechanical handling resistance. And quite often we'll have some spare cores within the umbilical as well to make sure that if something is damaged, we can carry on operating. And flying leads are very similar to umbilical, but often, and hydraulic flying leads, there's no armoring, and quite often they're kind of wrapped together for ease of installation. So umbilical installation, we can either, as with reel lay, they're either taken out on a large reel, drill, taken to site and installed, or for larger diameter umbilicals, you can use a vessel that has a carousel. So a reel is a vertical vertical hub, whereas a carousel is horizontal, and it's usually within a hold of a ship. So you can take a lot longer lengths. And typically you might want to bury your umbilicals, so you can install them within a pre-cut trench, or in some cases you can simultaneously lay them and trench them boarded in a basket, as you can see here, and then are pulled into place using either a diver or an RFV. And these are examples of the tutus, the topsides umbilical termination units are these two here. So you can see it just brings all the cores of the umbilical together, different type of combination here. And this is a subsea umbilical termination unit. Again, terminates all the various hoses and allows for distribution going onwards. So these are the subsea distribution units. So if we've got, if we want to connect, if we've got a single umbilical, excuse me, and we want to connect it to a number of different fields or different wells, then we can have these distribution units. So effectively, you can think of them as a junction box. So you'll have the main umbilical coming in on one side, and you'll have power or hydraulics or comms or chemicals or whatever being located in being sent off to a different direction. So I just want to finish up with touching on sort of a little bit about system engineering. So the we have all these kind of building blocks, and the real kind of art, should I say, is kind of combining these building blocks together in the most efficient way. And as always, there's more than one way to design a field or to lay things out, and it really depends on the individual circumstances. So, when we're starting off designing our, do we use manifolds or templates? Where are the top hole well locations? Do we need to test the wells? Do we need round trip pigging? How do we route the pipelines to where they're going? What size do the lines need to be to make sure we have sufficient pressure? Do we need to inject chemicals? Where do we need to inject chemicals? How do we provide for those chemicals? So it really is kind of wise to take a holistic approach to this subsea field architecture. So the overall kind of system design and just this little graphic together of some of the things that you need to think about that will provide input into the kind of decision making to come up with the overall system design. So that's it. That's been a very quick introduction to subsea umbilicals, risers, and flow lines. If you have any specific questions, I'll be happy to take them.
Yes, we're happy to take questions now. Unfortunately, Dem, it was hit and miss with the audio throughout the session. Unfortunately, probably about 20%. I've suggested that we'll post the video, and if anyone has any questions, we can, on this or on the video itself, we can answer them through email, or unless you want to ask any questions now.